Good afternoon. Thank you very much for joining me. For those of you who might not have seen me before, my name's Simon Brown. I'm the author and co-author of a bunch of software architecture books, and of course I'm the creator of the C4 model for Visualizing software architecture, which is what we're going to be talking about today. If you want to find more information about me online, you can go to my website, simonbrown.je. The .je is Jersey. And if you're on Blue Sky, you can also find me at the same location. So we're going to talk about the C4 model for Visualizing software architecture today. I'm going to show you this code later, which is going to allow you to buy my books at a quite big discount. But this URL expires midnight. So I am going to show you this at the end. So what's the point of this talk? Well, if you want to move fast as a team, you need some degree of alignment. And really, alignment comes through good communication. So in other words, if you want to move fast as a team, you need good communication. And unfortunately, this is where we go badly wrong in many cases with regards to things like software architecture diagrams. So I've been running software architecture diagramming workshops all around the world for the past 10 or 15 years. And I've seen lots of very, very horrible diagrams. For example, so this is just a bunch of technology choices in boxes for some reason. This one here it's boxes and no lines because it has boxes, but there are no lines linking stuff together. We also have an ASP.NET application doing something and a bunch of database looking things at the bottom. So this is kind of missing a big part of the structural story around software architecture, of course. This one's quite common. This is what people tell me is the functional view of their architecture. And it's just a bunch of stuff in different colors. And nobody knows why it's in different colors. It's probably just different people had different marker pens. This next one is my favorite. This is the type of diagram that starts out nice and neat. And then as you add conversations and you bring new people in to look at the diagram, you add more lines and more lines and more lines. So this thing here is like Frankfurt Airport, right? It's a big hub. From Frankfurt, you can go to lots of other places around the world. Just a mess of different colors, lines. That says UI upside down. Someone just kind of reached over just lazily and drew that box. It's not particularly helpful. This one here, if you take a photo of this and put it in your documentation, your job is done. You could say this diagram represents everything you are ever building. So this red box here around the outside, that's your system boundary. Inside your system boundary, you transport data in and out. You deal with errors, you schedule jobs and make reports for people, and you do some degree of business logic. Yay. It doesn't even say business logic, it says bus logic for some reason. It's not as if they can just use a smaller font. So this is super generic, doesn't really tell you anything about the business domain here. This one's quite funny. This is what people tell me is their high-level logical architecture diagram. And again, it's just a bunch of boxes with lines between them. Now, there are two things I like about this diagram. Number one, these little hops. I see this a lot when I work with software people who are also electrical engineers because they don't like touching wires, because that's very bad. And the other thing I like about this is, so this diagram was created during one of the design exercises, and in the requirements, security is important. As you can see from the box labeled security in the middle of this diagram. So this group realized security was important, put that box in the middle, but they don't tell you anything about security. Is this authentication, authorization, confidentiality? Who knows? This one's quite funny. So there are actually two things I like about this picture. The first is you can see very clearly there are three major building blocks to this system. There is a web application over here, there's a batch process over here, and there's a data store. So that's nice. I can also see the major responsibilities of those building blocks. So the web application allows people to get reports and edit some risk rules. That's in the requirements. The batch process is doing all of the importing data, running calculations, generating some reports in this case. That's nice. And we can see the list of things being stored in the data store. My issue with this is it's missing technology choices. And I think that's a shame. You know, I consider technology choices to be architectural decisions. They are things that are expensive to change later. You know, if you decide to build a Java application, Once you have 10,000 lines of Java, it's hard to change that to C# or Ruby. So this diagram is missing something about the underlying technology decisions, the architecture decisions. This one here is interesting because I think in our current fashion and trend, a lot of people will look at this diagram and assume it's a bunch of C# microservices. And I don't think that's the case. I think this is really a monolithic C# application talking to a database. So I think what this diagram is doing is mixing different levels of abstraction and not being particularly clear here. You've seen my favorite diagram. This is my second favorite diagram. You're like, wow, please don't show us this ever again. It's all one color. It's red. It's very shouty. It's got lots of funny symbols. This is showing a more complicated, event-driven, message-driven style of architecture. And you can see there are lots of different paths through the application. Success, reject, and so on. No matter which path you choose, you end up dying and falling into the trap. All arrows lead to the trap on the left-hand side here. This is a great example of where you want different versions of the same diagram, one for the happy flow and one for the exceptional flows, for example. Something I like on diagrams are people. Some representation of human users, because then we can see how the systems we build fit into the world around them. But please give them a name. Otherwise, they're just like stormtroopers, faceless, anonymous clones attacking this poor reporting service. So I want to know who these people are and what types of things they might be doing with my software system. If you don't have access to a whiteboard and somebody forces you to use a piece of paper, this is what happens over time. We add this box down here. No, we don't need it. Cross it out like a school teacher would. Big red cross through it. And then we cross out that red line with red and then put it back in red, which is very confusing. And we have this long-running joke in the industry that naming things is hard. Take this a few steps further and you get an even bigger mess. Right? So those are some of the example diagrams I've seen during my travels running software architecture diagram workshops. One of the things people used to ask me after the workshop was this: is this a tooling problem? If you let us use a laptop and a tool like Visio, do you get better pictures? And the answer is not really. You get visually nicer looking pictures, but you have the same issues. So go do a search on Google for software architecture diagram, and you'll get a bunch of pictures. These look nicer. Nice colors, nice fonts, nice straight lines, rounded corners, gradient shading, corporate color schemes, but they look visually nicer. They essentially have the same issues as the pictures I've already shown you. It's boxes and no lines. It's shapes, we don't know why. Sizes of boxes, we don't know why. Unlabeled arrows, we don't know why. Acronyms, all the rest of it. So they have the same essential set problems. Now, some of you who might be students here, you might be thinking, well, hang on. What's happened to UML? Because UML was supposed to be the thing that we use as software developers to draw architecture diagrams. Unfortunately, not many people are using UML today. There are some exceptions. If you go to Germany, you get a few more. And there are some cities in the Netherlands where you might get a few more. But on the whole, very few people are using UML these days. Why? I've heard all of these things literally said to my face. If you use UML here, you'll be seen as old and old-fashioned. I was the oldest person in the room, by the way. People tell me UML is too detailed. And of course, UML is a language. It has a 800-page specification, but you don't need to use all of the language. You can use a subset of the language. The problem is there is something about UML. People want to get it right. So imagine you're drawing a class diagram and you want to model a relationship between the two classes. Should you use the black diamond or the white diamond? You're like, I don't know. I didn't know there were diamonds in different colors. So then you go and look up what these diamonds mean, and it's composition, aggregation, or whichever way around it is. And then you've never heard of those terms. So then you look those up in a dictionary or Wikipedia. And then you end up on a website and it says things like this. Imagine you have a car and it has 4 wheels. If you destroy the car, do the wheels get destroyed? Like, I don't know. All I want to do is draw a line between two boxes on a class diagram, and now I've gone for a day and a half trying to figure out composition versus aggregation. And it just seems too much for a lot of people. And then, of course, we have the whole Agile thing. UML is not a part of Agile. It's not expected in Agile, which is all just nonsense. So that's problem set number one, I guess. One of the other big issues I see with things like software architecture diagrams is you'll have these organizations and they'll spend hours and days crafting beautiful looking architecture diagrams. And then you go and ask the developers a single simple question. Do you find these diagrams useful? And the developers say no, because they don't match our code. Great. And I see this time and time again as well. So one of the things I want to do here is I want to make it so that our architecture diagrams do map onto the real world. Right? If the diagrams are lying, they're basically useless. This whole phenomenon, by the way, is what George Fairbanks calls in his book, the model code gap. And the model code gap goes like this. When we're having a discussion about architecture, we have a bunch of words that we use. Modules, components, services, microservices, subsystems, layers, and so on. We have a number of words to use. We have a number of words we use to describe architectural building blocks. The problem is the languages we use do not have these same things as keywords. So imagine you are building an application in a language like Java, and you consider that application to be, from a top-down perspective, components organized into layers. The Java language does not have a component keyword. You can't do public component X in languages like Java. Similarly, languages like Java, C#, etc., don't have a layer keyword. So this raises an interesting question. How do we as developers create components organized into layers? And the answer is, it's up to us. Right, it's naming conventions, it's packaging conventions, it's build module conventions, it's all sorts of stuff. And every team's going to do this differently. So the model code gap, to come back to this, we have a view of our system from a top-down perspective, all these big, wonderful abstractions. But from a bottom-up perspective, when we look at the code, we can't find those same abstractions easily. So the two mental models of our system don't quite match. The model code gap. It's vocabulary. I think the biggest issue here is one of vocabulary. We don't have a good set of common words to describe architecture. We do have words like component, and you can go and look up the word component in the UML specification, and it says this: a component is a modular unit, I'm happy with that part, with well-defined interfaces, that's good as well, that is replaceable, fine, within its environment. What? What does that mean? We can use this same word to mean all sorts of things at different scales and levels of complexity. And it's just too vague. So that's part of the issue here. And of course, people don't want to use UML for all of the reasons I've just mentioned. They want to draw boxes and arrows pictures. So my perspective, and this is where C4 comes into play, is if you don't want to use UML and you want to use boxes and arrows, but you want to draw some nice architecture diagrams, that's fine, but try to introduce some degree of structure from an abstraction perspective and use a self-describing notation. So make sure your boxes and your arrows and your colors make some sense. And I like to summarize this with this slide. A common set of abstractions is much more important than a common notation. So UML gives you all of these things, but people don't want to use it. They find it confusing. They get stuck. So I think having an abstraction-driven approach is potentially much more useful today, given our lack of maturity, than having a standardized set of boxes and arrows. I would love a standardized set of boxes and arrows, by the way, but I don't think that's practical today. So this raises the question, what are the abstractions? What do I think we can use to describe most software systems out there? And this is the set of abstractions I came up with all those years ago. So the top one is what I call a software system. This is the hardest of these abstractions to easily define, but a software system is typically something that a single team is building, is something that a single team has ownership of, and it's something that a single team can see the internal implementation details of. So I might be building a software system called A, and I have a dependency on a software system called B that you folks are building. So we have our own perspective on the world. I want to know my internal implementation details. I don't care about yours. And the reverse is true. So there's typically, not always, there's typically a link between a team boundary and a software system, the thing that that team is producing. So that's a top-level abstraction. And you'll see an example of this shortly. When we pinch to zoom on that software system and look at the internals, I'm going to say a software system is made up of one or more containers. Now, who knows Docker? Right, forget Docker. Right, this has nothing to do with Docker at all. There's an unfortunate clash of naming. I got the name first, true, and irrelevant. Because I came up with this naming before Docker. Docker's way bigger, more popular. So by container, I basically mean an application or a data store. So the software systems we build are made up of applications and data stores. I'm calling those things collectively containers. So what do I mean by an application? I mean an Angular app running in a browser, a React app in a browser, a mobile app on a mobile device. It could be a server-side app running in a web server, Spring MVC, ASP.NET MVC, Ruby on Rails, a C++ app on a server, a shell script. That's what I mean by application. And from a data store perspective, it's a relational database schema, a bunch of tables, etc. Folder on a file share, Amazon S3 bucket, Azure blob store container. That's kind of what I mean by data store. So the software systems we build are made up of one or more applications or data stores. If we zoom into the applications, I'm going to say a container contains components. That's where the naming comes from. So I did just say components massively overloaded, and it doesn't really make sense. I want to try and put some more precision around the word components to mean this. The component is a grouping of related functionality, nice, clean, well-defined interface, running inside a container. So I want to be specific and precise about the levels of abstraction here. So the implication here is that components in this set of abstractions are not separately deployable, runnable things. It's the application, it's the container that's the deployment unit, essentially. And again, you'll see this when I show you the examples. Zoom into a single component, and it's basically made up of code. So if you're building a Java component and zoom into it, it's made up of classes, enums, interfaces. C#, same thing. C++, same thing. Languages like JavaScript, functions, objects, classes, like JavaScript keeps adding all the things, but hopefully you get the point. So that bottom level represents the constructs we have in the languages that we are using to build components. And that's it. So a software system is made up of one or more containers. Containers contain components, components built from code. That's the set of abstractions. And I find you can describe most software systems of various scales and complexities using those four abstractions. Diagrams. So once we have a set of abstractions and we know how to think about the things that exist in our architecture, we can draw some diagrams. And this is where the C4 model gets its name from. So C4 is actually named after the static structure diagram types. If you want to know more about C4 afterwards, you can go to the website, c4model.com. The example diagrams I'm going to show you are also available on that same website. So C4, context, containers, components, code. That's it. It's 4 levels of diagrams that map onto those 4 levels of abstractions. So we're starting with a very high-level diagram, and we're basically doing the Google Maps pinch to zoom movement to drop down the levels of detail until we get to the code. So I'm trying to do 2 things here. I'm trying to make diagrams that reflect reality, and I'm trying to fix the model code gap so we have a way to go up and down the various levels of abstraction without breaking our mental models. And the concept here is diagrams as maps. So I live in Jersey in the Channel Islands, and if you open up Google Maps and you do a search for Jersey, you're likely going to get that picture. So Google Maps makes Jersey as big as it possibly can. Now this is great if you want to know where the airport is and how to get to the main town where your hotel is. If you've never heard of Jersey before, this is too detailed too quickly. Imagine you join a new team and they've got a million lines of code and say, oh, just go add this feature here. You're like, well, that's too much detail. How do you fix this issue? You do the pinch to zoom out movement. So if you pinch out and zoom out a little bit, Jersey gets smaller And now you can see there's another island next door called Guernsey, and this land you see here is actually the coast of France. If you zoom out further, Jersey disappears entirely because it's only 15 kilometers by 10. It's a tiny island. The reverse is true. If you keep zooming in and zooming in, eventually you'll drop into Google Street View. And Google Street View is a one-to-one mapping of the real world when the photographs were taken. And I essentially want to do the same thing with architecture diagrams. I want different levels of diagrams that allow me to tell different stories to different audiences. So the high-level diagrams are great for all audiences, whether they are technical or non-technical. As you pinch to zoom, you're getting more and more and more technical information. So down here at the bottom, it's really just developers and architects. In the middle, interesting bunch of audiences potentially. Infrastructure staff, operations staff, DevOps people, network engineers. So there's some interesting audiences in the middle, as you'll see shortly. Now, I do need to say this because it's important, and everybody ignores this part and they forget it. Although C4 has the number 4 in its name, you do not need to use all 4 levels. Right? Most organizations only use levels 1 and 2 right at the top. Right, this raises a few questions. Why am I telling you this? So first of all, there are lots of people on the internet who say, well, C4 looks great, but it forces you to draw 4 levels of diagrams. And that's too much. And I agree. The top 2 levels you can draw quite quickly, and they don't generally change rapidly. So the context diagram basically shows the system you are building as a team and the world around it in terms of people, so your users, and other systems that your system talks to. That generally doesn't change rapidly. The container diagram showing applications and data stores also is quite static. It's quite slow moving, unless you've got a very big microservices architecture or you're using lots of AWS Lambdas as your function apps, for example. But in most cases, the container diagram ages quite slowly. Once you get down here, levels 3 and 4, every time you add a feature, these 2 levels of diagrams potentially need to change. So that's the thing you have to bear in mind here. So this raises more questions, unfortunately. Are these 2 levels valuable? Yeah, they are. If you are designing a small monolithic application, maybe sketching out up front your component model might be a useful thing to do. So you can allocate different components to different parts of your team. If you inherit a monolithic application and you don't know how it works, maybe automatically generating a component level diagram is helpful for you to navigate that large and complicated code base. The problem here, of course, is that automatic generation is hard at this level. It's easy here, but it's hard here. Why am I saying this? If you have a nice convention where a single folder in your code base maps to a component, in many IDEs, you can right-click that folder and say, generate me a class diagram of the code in this folder, which means you can generate this lower level really quickly. You can get that detail on demand. This is trickier because of the model code gap. Because we're all using different conventions for defining components, whether it's naming conventions or packaging conventions or namespace conventions or build module conventions, you need to teach your tooling how to reverse engineer your code base and then look at all the classes and start grouping classes together into components. That requires some effort, and therefore you have to work out, is the effort I need to spend doing that worth it? Am I going to use the diagrams afterwards? In some cases is yes, in many cases no. So this is a very long way to say, start with the top 2 levels and look at these if they add value. This raises a follow-up question, which is, well, hang on, why is this called C4 and not C2 plus 2 or some other like combination of letters and numbers? And the answer is the model code gap. If I presented the top 2 levels on their own, you're now missing a connection to the source code. So that's why I have these levels here. They allow you to track from the top all the way down to the bottom, but you don't need to draw diagrams at that level of abstraction. That's the short answer. So let's look at some actual diagrams of this thing. So imagine we work for a bank and we've been asked to build an internet banking system. We're going to draw a bunch of C4 diagrams to represent that internet banking system, and you can find those diagrams on the C4 website. So this is the starting point for my diagram. We're going to draw a system context diagram for the internet banking system. So I've got a box in the middle representing my internet banking system. To draw the rest of this diagram, I need to ask two questions now. Number one, who is using that? So who are my users, my roles, my actors, my personas? In this example, there's just one type of user, and it's all of us as personal customers of the bank. And we are going to be using the internet banking system to view our account balances and make payments online. Right. For most systems, you have lots of different user types, but in this case, there's just one. So that's question one, who are our users? Question two is, what are the system-to-system integration points we need to support? As a team building that blue box, we do not want to build a gigantic database of customers, accounts, and transactions. We're not building a bank, we're just building the internet banking system in an existing bank. So let's assume the bank has this data already. Where is it being stored? In their existing mainframe banking system. So we're going to use that, pull information out, present it on the web. We also need to send emails to our customers so they can do password resets, multi-factor authentication, fraud alerts, whatever it might be. We don't want to build an email delivery mechanism. We're just going to use the bank's existing email system, which in this case is Exchange. And that's my context diagram. It's showing you the system we're building, who's using it, and how it fits into the other systems and world around it. Don't worry about colors and shapes and arrow directions. The C4 model does not prescribe any particular colors and things. Essentially, the gray boxes represent existing systems, and all arrows look the same. So you can apply whatever notation you want, just make sure it's described with the diagram key. So that's our context diagram. It's a nice start. Now we can pinch to zoom on that blue box, the internet banking system, drop down to level 2 and draw a C4 container diagram. And it's literally just the pinch to zoom, open up that box and show smaller boxes inside it. And this is the start of my container diagram. This empty box here represents the internet banking system box from the previous diagram. We still need a user, and we still need our two external systems. So we're telling the same story at a lower level of detail, so therefore we need the same things on the diagrams. And this is a characteristic you'll see of C4 diagrams. You end up copying and pasting boxes across diagrams. So now we can start our story. You go home, you open up your laptop, you go to mybank.com/internetbanking, hit enter. That request your web browser makes goes to and is serviced by that server-side web application. This is a Java Spring MVC application, and all it does is send back static content to your web browser. Once that content lands in your web browser, what you have now running in your web browser is a single-page app. So what I'm trying to do here is I'm trying to show you a snapshot of the system when it's running. I get from a deployment perspective, we take all of those two things and put it on one file and stick on a server. And that's interesting, but I'm trying to show something slightly different here. Imagine the system's running, you take a snapshot, that's essentially what we have. We have some code running on a server and some separate code running on a client-side device. So we have our first UI. Let's also build a dedicated mobile app for our customers. So this is not a shared code iframe thing. This is a dedicated mobile app. And we're going to use the cross-platform Xamarin framework, now called Maui. Two UIs. We want to get data from this thing here. So we go and visit this team who say, hey, we know you have an API. Can you please stick it on the internet? They're like, no, for a whole bunch of security reasons. Right. So we are going to need to build something that we can call, and it can call the mainframe banking system, and then we can put DMZs and firewalls around that thing. So we're going to build a single monolithic API application. It is going to expose a bunch of APIs, JSON over HTTPS, to those two UIs, and it will make calls to the mainframe banking system for us. In order to sign in to the internet banking system, we need like a username and a password. So we go and visit this team and we say, hey, us again. We know you have customer records. Can you please add a password field? They're like, no, go away. This is written in COBOL. We have one COBOL developer. It's not possible to change it. Right. And that's the sort of thing that happens in the real world. So we're going to have our own database schema. The bank uses Oracle. They have an Oracle license. Let's put all data in Oracle. And that is my container diagram. It's showing you that there are two separately deployable Java applications, two UIs, one's Angular, one is a mobile app, and a database schema. So this diagram is showing us the high-level building blocks in terms of applications and data stores. It is showing us the high-level technology choices. It's showing us something about the responsibilities. So you'll see the additional text on the diagrams here. It's showing us something about the responsibilities of those boxes. And it's also showing us something about the container-to-container interactions, the intent, and sometimes the protocols and technologies. So it's a really useful diagram from an architecture and developer perspective. It is missing anything about clustering, scaling, fault tolerance, anything about deployment, anything about cloud architectures, firewalls, DMZs, subnets, VPCs, all of that stuff is completely missing from this diagram on purpose. Why? If I'm a developer, I want all of those 5 things running on my laptop in some form, so I can do local development, local debugging. A live production environment takes those 5 boxes and sprays them across clusters of machines, whether it's on-premises or cloud. So not having deployment information on this diagram gives me the flexibility to show multiple deployment topologies really simply. And I'll show you some examples of those later. Just to complete the story, we'll take the API application box at the bottom. We'll do the pinch to zoom in movement, drop down to level 3, draw a component diagram. It's the same deal. So you take that box, pinch to zoom, and show smaller boxes inside it. This empty white box represents the API application container. It is used by the things at the top, and it uses the things at the bottom, so they're repeated from the previous diagram. And now we start the story. You go and sign in, you add your username and password, hit enter. Both UIs make an API request. That is serviced by the sign-in controller component. It then uses a security component that checks our credentials and issues a session token. Then you become signed in. Then your two UIs can ask for a list of your accounts. That's this side here. And then if you forget your password, there's another API call. So what we're now showing are the high-level code structures that exist in your code base. In other words, if we were to build this application, I would expect anybody on the team to be able to find these 6 boxes super quickly. So if you are building an application which is components in layers, this diagram shows you components and layers. If you're doing ports and adapters or hexagonal architecture, this diagram shows you those concepts. So it's showing you high-level code structures and also some of the lower-level technology choices that we're making now. To complete the story, we'll take this mainframe banking system facade box, drop down to level 4, draw a code diagram. It turns out once you get down to level 4, just use UML. And I know people hate that as advice, but just use UML, especially if you are using Java or C++ or C# or another OO type language. So either automatically generate this level of detail or draft up something that says this is the high-level set of code things that exist in that component boundary. In terms of notation, up to you. You can use different shapes, different colors, entirely up to you. Quick fun fact for you, quick little side story. If you go to the C4 website and you look at the example diagrams, you're going to get green, blue, or red examples. If you go back the next day, you'll get a different color. Right? And I did this recently on purpose because, as I showed you, the example diagrams are blue and gray boxes. And therefore, the website only had those blue and gray box examples on the website for a long time. And there are lots of people on the internet who now say C4 looks boring because it's all blue and gray boxes. I'm like, really? It literally says on the website, use whatever colors you want to. But everybody chooses to use the blue and gray. If you look at the templates for draw.io or Visio, they also use blue and gray boxes. But you can use any colors. It's entirely fine. You could also use UML. You're like, please stop saying this. Right? But if you want to use UML, if you want the richness of the UML notation and all of its semantic goodness, if you want lots of arrowheads, feel free to use UML. There's nothing wrong with that at all. Why is this possible? C4 is essentially 2 things. It's a set of hierarchical abstractions and a set of hierarchical diagram types. That's it. you can plug in UML as your notation if you want to. Nobody does that, but you could if you want to. If you go to the C4 website, you'll see there are also 3 other types of diagrams defined. The first diagram type is what I call a system landscape diagram, and it really just shows you more systems and more people within a specific organization, enterprise, group, department, whatever it might be. So here is a partial system landscape diagram for the bank. I'm using this dashed line to represent the boundary of the bank. So all of the systems here sit inside the bank, and our users sit outside of the bank. And I'm showing you how users interact with ATM machines and the internet banking system, and how their customer support staff are using the internet banking system. So, it's just how customer support staff are using the mainframe banking system. It's just a useful map of systems. What many organizations do is they'll draft up something like this. So they'll have a map of the important systems in their landscape, and then they'll make that interactive. And when you double click one of those systems, it takes you to the C4 diagrams for that particular individual system, which is quite nice. You'll also see there are something called dynamic diagrams defined on the C4 website. So the static structure diagrams are super useful, but they don't tell you how an individual feature works. So for that, you could use something like a UML sequence diagram. So this is describing how the sign-in feature might work for that internet banking system. If you've not seen a UML sequence diagram before, basically it's a bunch of things interacting at runtime, and time goes downwards. That's all you need to know. So follow the lines, time goes downwards. That's option 1. Option 2 is a free format version of this, which is the one you'll see defined on the website. And it's just a free format version of the sequence diagram. It's the same set of elements collaborating at runtime, and you'll notice there are, where's my pointer gone? There it is. You notice there are numbers on the arrows representing ordering. So you just basically follow the numbered ordered arrows. Diagram type number 3 are the deployment diagrams, and this is where you map the C4 containers or potentially C4 software systems onto things that exist in the infrastructure world. So here's an example of a deployment diagram for the internet banking system. Imagine this is a development environment. So what this says is I have a developer laptop. On my developer laptop, I have a web browser installed locally. That's where the single page application runs when I'm doing local development. I then have 2 Docker containers running. So we should bring Docker back into this, of course. We have 1 Docker container running Apache Tomcat, and that's where I'm deploying both of those 2 applications so I can conserve memory and resources. And I have a second Docker container running Oracle, and that's where my development database schema is running. In order to do end-to-end testing and integration testing, I also need a development copy of that mainframe banking system. I know that inside the Big Banks network, there is a server called Big Bank Dev 001, and that's where the system is running. So the blue boxes are instances of containers, and the gray box is an instance of the software system. I'm cheating. I'm using abstraction to my advantage here. So the blue boxes I care about, the gray box I don't. Underneath the covers behind this, it could be file systems and COBOL apps and all sorts of stuff I know nothing about. But from my perspective as a developer on the internet banking system, I know that I can point my application to Big Bank Dev 001 and magic happens. So again, you can use abstraction to your advantage if you want to. AWS, Azure, Google Cloud, Docker, Kubernetes, you can also weave these concepts and use all the nice icons and create some kind of nice but useful looking architecture diagrams for cloud architectures. So this is basically showing you we have a web application and a database schema deployed onto Amazon Web Services, and we're making use of Route 53 for DNS routing, Elastic Load Balancing, and you've got the web application running on an Amazon EC2 server in a load balancer in an auto-scaling group. Couple of FAQs to finish up with, because there are a couple of things that trip people up when they look at C4 for the first time. And the first of these is message-driven architectures. A lot of people instinctively want to draw that type of diagram. So imagine we have a service-based architecture. We have a bunch of services A and B on the left-hand side that are producing messages. They're going into a bus, and that bus is forwarding messages to services C and D. this kind of makes sense. This is true. This is factual. This is accurate. But the problem here is most message-based architectures look like hub and spoke architectures. They're fan in and fan out. What happens in many cases is actually this. You have a point-to-point coupling between two services via a queue or a topic. So the difference between this example and this example is I'm modeling the queues and the topics as C4 containers, not the message bus. So why am I doing this? A queue, a message queue, is essentially a data store. It's a bucket. Some processes put messages into the bucket and other processes pull messages out of the bucket. In this example, we have two queues, X and Y. This tells you nothing about deployment. At developer time, I want those two queues running on a single message bus on my laptop. A live production environment could see each queue on a separate messaging cluster, broker, whatever it might be. So again, we're not telling anything about the deployment here. So that's option one, model your queues and topics as C4 containers. If you do have a genuine point-to-point connection, you could also leave out the middle box and you add via queue X or Y on the line like that. So that's a visually simpler approach. The trade-off is that some people might miss there's a queue in between. But you could use different color coding, different arrows to dictate this is a message-based interaction. That's fine. In terms of arrow direction, you'll notice all of the arrows have gone from the left to the right, like sends message to. You can also start experimenting with different arrow directions to make sure the text matches. So here we've got services publishing messages and services over here subscribing to messages from the queues and the topics. People ask me like which one is best. They're all fine. Like you can use any variation of these and I think they work fine. The bottom one, I think, with the arrows going subscribe from, I think works best if you have a one-to-many pub-sub type relationship. So that's message-based architectures. The bigger topic and the thing that trips most people up is, of course, our friend microservices. Now, I mean, step one, don't use microservices if you don't have to because it's hard. But if you are using microservices, people ask me, how do we model our microservices-based architectures with C4? And the answer is one of these three options. So there are lots of different ways you can model microservices architectures depending on your perspective. So I'm going to go through a bunch of examples very quickly, and I'm going to answer this question, what is a microservice anyway? So let's paint a scenario. Imagine we work for a small startup, we have no money, but we need to build a first version of our system to get customers. So we're going to go with a monolithic architecture. This is our context diagram. We are a team building system X, and it provides business capabilities A, B, and C. And there's one type of user. So that's our context diagram, nice and simple. Pinch to zoom, this is our container diagram. So we are building a single monolithic server-side rendered web application talking to a single monolithic database schema. So features A, B, and C are spread out across those two building blocks. All good so far? Nice. So that's version one. That's the monolithic approach. Stage two, we started to get some more money. We've got some more customers. And we started to realize that that monolithic application is slowing us down. We're getting merge conflicts. It's just hard work. So we want to start adopting a microservices style of architecture. I'm going to use this definition of microservices by James Lewis and Martin Fowler, which is essentially this. In short, the microservice architectural style is an approach to developing a single application as a suite of small services, each running in its own process and communicating with lightweight mechanisms. I'm going to change one word, which is that. So I'm going to say we're developing a single software system as a set of services to bring this back into C4 land. Our context diagram stays the same. We're one team. We're building one system. It's when we get into the details of that system, things have now changed. So we're still keeping our monolithic web application, and we split out the business logic into separate service APIs and each service API is looking after its own database schema. So now we've clearly split up features A, B, and C, and this is arguably a microservices architecture style. I've color-coded the pairs of boxes. So the 2 blue boxes are service A, the 2 green boxes are service B, and the 2 red boxes are service C. But this is not showing me that those 2 boxes are a microservice. So what you can do is add a border around those pairs of elements and say that we have service B here, which is a combination of the API and the database schema. So now we're representing a microservice as a group of C4 containers. We add new features, we add service capability D. Imagine D is implemented by a single stateless AWS Lambda written in Python. Now we can say that a microservice is essentially a grouping of one container, or it's just one container. So that's a couple of options there. Stage 3, we've got tons of money. We're going startup to scale up. We now want to split responsibilities across different teams, adopt Conway's law, etc., etc. I'm going to stay on team X and build the UI. So my context diagram is now different. I'm still building system X. I now have dependencies on all of these different services that you folks are owning separately and individually. My container diagram looks like this. It's a single monolithic web application talking to your services. If you folks are on the service A team, this is your context diagram. That's the thing you are building. So now we're representing your service as a software system. You have an inbound dependency from my system, and your container diagram now looks like that. So this is essentially respecting team boundaries, and we're not looking at each other's implementation details. That's the easiest way to remember this. So summary. That's your C4 summary. C4 is a set of hierarchical abstractions. There are 4 of them. A set of hierarchical diagrams. There are 4 of them. It's notation independent. You can use blue and gray, but also other colors are available. And by definition, it's also tooling independent. So thank you very much. Hope you found that useful. And again, there's the code for the books. Thank you.